Hello, everyone. My name is Sunandita Sarker. I'm a new MRC Fellow, and I work under the advisement of Dr. Ryan Sokol and Dr. Eleanor Tubaldi. So today I'll be talking about my upcoming project that I will start from this July as an MRC Fellow. And it's about manufacturing a soft robot with integrated fluidic circuitry for marine application. Currently, or traditionally, we are vastly dependent on autonomous underwater vehicles or remotely operated underwater vehicles. Autonomous underwater vehicles are mostly in a torpedo shape, and they have they're good for like long range of survey, and they have a propulsion engine that helps it to survey an ocean underwater or even the surface for a long range. But they don't have manipulators, so they cannot interact with the samples, or they cannot be used for collecting samples from from the seabed. On the other hand, remotely operated underwater vehicles, or ROVs, they can have, I'm sorry, I don't know why they are not playing. There's something wrong. Okay. The ROVs are, they can have manipulators. So you can use them for collecting samples or interacting with biological specimens. But the problem with ROVs are they're normally, because they're tethered, so they need to be, the working range is short, and they have a bulky structure, which could be difficult for reaching like underwater cave, or at the very bottom of the seabed where delicate specimens are present. So here in this video, you can see different industrial marine robots that is currently available for different kind of scientific exploration, and they are doing a very good job, but despite their different challenges. Another new there's been a new interest, a lot of interest with soft robots for marine application. Soft robots are compliant, they are very resistant and very versatile. So they have the potential to work in like uncertain environments, and we can use them for collecting samples without damaging the samples or having a harder impact on the environment. The robots that we are seeing in these videos, one of them are from MRC group. So most of them have outer, like softer material, but internally they're mostly controlled via rigid parts such as motors or like pneumatic actuators. That makes it like partially soft, but not fully soft. So the same problems that we have with like traditional rigid robots, that they still can cause like environmental damage, and they are hard to assemble because it needs to be like water protected and all. So my goal for this project is going to be to use additive manufacturing, especially multi-material additive manufacturing, to generate a new class of swimming robots that is fluidically controlled by integrated fluidic circuitry for both locomotion and buoyancy. So for this manufacturing process, we are going to use inkjet-based 3D printing or polyjet 3D printing. So this printing process is a lot similar to color printer, where materials are printed layer on top of layer to build a 3D structure. One of the special things for this type of 3D printing process is that we can print multiple materials side by side, and we can also print sacrificial material that can be dissolved or removed in future to get like hollow structure, which could be used for fluidic actuation. So the students of BAM Labs before has shown the capability of printing fully integrated robotics with fluidic circuitry for controlling different movement of a robot. So my concept is to leverage and extend those strategies to realize a new class of 3D printed swimming robots. And this robot will have integrated fluidic circuitry, similar to what like our lab has demonstrated before, but this one was limited by using only normally on fluidic transistors. That limits its capability, but extending those fluidic circuitry with other kind of elements such as normally closed transistor and also different including diodes and capacitors, we can get a full range of motion. At least we hypothesize that we can get a full range of motion that would allow us for locomotion of the robot. Additionally, we plan to include a buoyancy tank that will also be controlled via fluidic circuitry. And this buoyancy tank, we can control the ratio of water and air via peristaltic valves to realize the diving and the resurfacing motion of the swimming robot. So as I said, I am going to start this project in this upcoming academic year. So it's still on the stage of like designing. So I'm currently at task 1 while I'm designing the robot and the fluidic circuitry. Next would be to characterize and build normally closed fluidic transistor. That would be a big essential prerequisite for having such more complex fluidic circuitry, and then finally include that in our swimming robot. I would like to thank both of my PIs, Dr. Sokol and Dr. Tubaldi, for this opportunity, and MRC for this fellowship. Thank you so much.
Any questions for Sunandita?
Well, with that, if there's no questions, I'd like to thank you all for sticking around for the end of the day.